Okay, in this lecture what we're going to do is continue our discussion on time-dependent problems. We'll talk a little bit about the theory, then I'll show you algorithms on how you would implement this, particularly a little bit on harmonic or eigenmodes, and then I'll show you some specific algorithms for solving transient problems. Okay, so we're going to start out with general description. You've got some displacement or temperature. It's a function of space in 1D and time. So we approximate it with our finite element nodal solutions, or finite element solutions in space and time, which includes decoupled nodal solutions that are time dependent. And here's your interpolation functions, which are only spatially dependent. So it's a decoupled method. This is typically what's used in most cases. So you've got these time-dependent solutions at each point, and we're going to interpolate between them with the interpolation functions. These are no different than we've studied before. Alright, so we take our ODE, put it in a weak form. We get this, which you should be familiar with now. It's based on this ODE here, first order time derivative. In comparison, the weak form for the hyperbolic equation includes this wave term. So this gives harmonic behavior. This is damping. So these are losses. Anytime C1, your damping coefficient is not 0, you're going to generate losses. When this term goes to 0, it's a fully conserved system. Energy is going between kinetic and stored elastic energy. And over here is your boundary condition. So if you have a load on the end, that's where this gets implemented or introduced. Here's the strong form of that equation. So you can also think of this, if you're more familiar with dynamics of low parameter systems, this would be mx double dot mx or cx, and this would be a spring kx term and a forcing function. Okay, so given these ODEs, I want to talk about time stepping, and there's some flexibility on how you can implement time stepping. If you're particularly, now we're really getting into transient problems. So here is a case where you have a nodal solution, let's just say for now displacement. So you have displacement of future time step minus current time step over a delta t increment in time. And that's equal to the following weights of the velocities based on whatever alpha is. Alpha may be anything between 0 and 1. So we're defining US as my displacement at the time step S. So TS is going to be a summation of these discrete increments. So delta t is basically the difference between the current time step and the previous time step. So you sum all these up and that gives you the current time. If it's equal time steps, it's just the number of time steps times delta t. This is just the more general form. Alright, so let's look at the following form. We have this velocity at some incremental time ahead, alpha. We're saying this is the difference over delta t. So we rearrange this. Remember, this is a form of Taylor series. And we're defining this as our velocity as a weight function on alpha. Alright, here's the most important part of this. What do we define as alpha, and how does it impact the solution? One option is let alpha be 0. This is sometimes used, it's called forward difference. It's conditionally stable, and it has order delta t. I mean conditionally stable, if you make this too large, as you step forward in time, this will go unstable if this is too large. If alpha equals 1, it's called backward difference. It's stable and it has order delta t accuracy. And here's the form. Crank-Nicholson is if alpha equals 1/2. But not only is it stable, but it's order accuracy delta t squared. This is most commonly used. It's more accurate and it's stable. Alright? Discretization. So for the parabolic equation, we can put this in the finite element, and you get this form of the equation after we take the integration of our weight functions. And let's look at stability. Let's say alpha is less than 1/2. In that case, your critical time has to be less than this following relation. And notice this depends on your eigenvalue, where this is the largest eigenvalue. Right? So we set this problem up here. In the case where this is 0, we can solve this by taking the determinant. And you have to be careful with the size of the mesh used. One thing to keep in mind on the size of these meshes is if you continue increasing your mesh density, you can resolve more modes, but usually these higher order modes become negligible in terms of the amount of energy they'll carry. Usually the first few modes are the ones that are most commonly seen in engineering structures. So an overkill on a large mesh is often not necessary. Alright, so time-dependent simulations. So given this parabolic equation again, we've shown this form here. You can also just normalize it with C1. This is the form that's commonly used, where this is your time constant of the response. If you think in terms of a thermal time constant, if I put a thermocouple in water, it's going to take a certain amount of time to reach steady state. It's based on this parameter. Alright, now let's really just focus on taking the, here we take ui plus 1 minus u over, I'm taking the average of fi and fi plus 1. Keeping in mind, I is my current time. So at this point, we're just going to take this equation and rewrite it time. There's other ways you can approximate that by just assuming you only know force. Get it into this form, or simplify in terms of A and B, same behavior of u if you know the time constant and the forcing function. Some delta t, the range of time from 0 to t at final time. And we're going to do this for a 0-4 condition for u. I believe somewhere in here you want to put initial condition for u. So what I recommend trying is set this up, use initial condition unstable.